Welcome, students. So, we will continue our discussion regarding signal space and geometrical representation of signals. So, in the last video lecture, we stopped at this point. So, we discussed how, given any signal in time domain, how we can represent them as vectors in the signal space. If we can find out two vectors phi1 and phi2, then we can represent the signals in terms of those two vectors or as a linear combination of those two vectors. In fact, any signal can be represented as a linear combination of not only two vectors phi1 or phi2 but can be more than two. So basic idea is that a signal in time domain can be represented as a vector in, let's say, two-dimensional vector space defined by phi1 and phi2, or a three-dimensional vector space defined by phi1 phi2 and the third vector phi3, and so on. And we can generalize this concept and define any signal in a n-dimensional vector space or a n-dimensional signal space, provided that we can find a set of orthonormal basis functions, phi1 phi2 up to phi n. So phi1 phi1t, phi2t up to phi nt, such that these basis functions have some properties which is their norms for any phi I is equal to 1, and for any phi I times phi j integrated over all values of phi I and phi j gives you 0. So basically this is equivalent to the dot product. If you imagine phi I and phi j as vectors, and this is equivalent to the norm or the energy. So if these relations hold, then we can represent any signal as a linear combination of this phi i's or phi up to phi 1, phi 2, phi 3 up to phi n. And then for a special example of a two-dimensional signal space, we can represent it using a set of axes along the phi 1 direction and phi 2 direction, and then we can have the signals s1 and s2 defined as vectors with their corresponding projections on the phi 1 axis and also the phi 2 axis. So now the question where we stopped at the end of the last video, the question is how to choose these functions. So given a set of signals s1, s2 and so on, how to choose these phi 1s and phi 2 so that they follow these properties, and then you can define the signals in a signal space spanned by these phi 1, phi 2, or maybe phi 3, phi 4 up to phi n. So that can be done by a simple algorithm called Gram-Schmidt Orthogonalisation. So let's imagine that you are given with a set of signals. Okay, let's say you have S1T. So let's generalize this. Instead of two signals, which is necessary for binary communication, we can have many signals. So S1, let's say we have a given set of signals S1, S2 up to, let's say, Sn. So we have n signals, and our goal is to find out a signal space where we can represent all these signals in the same signal space. So that signal space can be a two-dimensional signal space with two dimensions, phi1 and phi2. It can be a three-dimensional signal space with three dimensions, phi1, phi2, phi3, or it can be an arbitrary n-dimensional signal space with phi1, phi2, phi3 up to phi n as the directions or the dimensions of that signal space. So the Gram-Schmidt orthogonalization procedure will give you not only the phi1, phi2, phi3, etc., but also the exact number of this phi n or the actual dimension also. So the Gram-Schmidt orthogonalization algorithm will stop when you have enough number of dimensions, phi1, phi2 up to phi n, which is complete or which is good enough to define this n signals. Okay, so let's say I have just to take a small example. Let's say I have S1 T and S2T, and let's say S3T and S4T. Okay, so let's say I have four signals, and whether I need two dimensions, phi1 and phi2, or I need three dimension, phi1, phi2 and phi3, this can be also obtained from this Gram-Schmidt orthogonalization. So your Gram-Schmidt orthogonalization algorithm will stop once you have a complete set of basis functions that are enough to define these four signals, let's say, or any arbitrary set of signals from S1, S2 to Sn. So to begin with, let's say if I have the signals, if I know my signals, if I know S1, if I know S2, if I know all the signals that I need to represent in the signal space, then the first step in the Gram-Schmidt orthogonalization is to initialize your phi1. So your phi1 is nothing but the signal S1 divided by the norm of S1. So you initialize phi1 as this. You have to start from somewhere. So this is the start. So you get phi1. So basically you define your phi1, which is an unit vector, unit basis vector, that is within or that is along the direction of your signal S1. So you are initializing your phi1 to be S1 normalized to unit energy. So S1 divided by the norm of S1 is equal to phi1. So in this case, you will see that phi1, if you take phi1 square and integrate it, so basically you will get S1 square. So basically this is again function of time. So if I don't write this t in the parentheses, it kind of implies that we are working with functions of time. So let's say S1 phi1 square dt integrated is basically S1 square dt, and then you have the norm of S1 here. Okay, so the numerator here is the norm of S1 itself. Okay, and then you have divided by the norm of S1, so this is equal to 1. So if you take the energy of phi1 or the norm of phi1, then you get 1. So this holds true. You remember that your phi1, phi2, phi3, all these basis functions, they should have unit norm and they should be orthogonal to each other. So So let's say phi1 is this, and that this unit norm property holds. Okay, so now what will be our phi2? Okay, so to calculate phi2, first we calculate an intermediate vector phi2 prime. Okay, so phi2 prime is basically S2 divided by the norm of S2. So remember, you know all the signals beforehand. You are starting with the inputs set of all these signals. So you know S1, you know S2, you know up to Sn. So since you know S1, you know S1's norm, and you quickly initialize phi1 as S1 divided by norm of S1. And then for phi2, you first define phi2 prime, which is S2 divided by the norm of S2 minus the projection of S2 divided by the norm of S2 on phi1. Okay, so what does this mean? This means that you have first defined phi1. So you are seeing that if your signal S2 has any component across the phi1 axis, okay, and you are subtracting that component from S2 divided by norm of S2, and that is your phi2 dash. And then let me just a second, let me erase this part. Okay, so you have phi2, which is this particular number phi2 prime divided by the norm of phi2 prime. Okay, so this is an iterative algorithm. You get phi1 as denoted here in the first step, then you obtain phi2 from your knowledge of phi1, and then you go on like this. You then find out phi3 prime, which is S3 divided by S3's norm minus the projection of S3 divided by S3 norm on the phi1 axis and the phi2 axis. Okay, so you have calculated phi1, you have calculated phi2, so you can calculate the projection of this S3 divided by S3 norm on phi2 and S3 divided by S3 norm on phi1, and then you are subtracting both these terms from this. Okay, and in that way you proceed. So once you get phi3 prime, you get phi3 as this, and in that way you proceed. You get phi4 prime, which is S4 divided by the norm of S4 minus all the projections of S4 divided by norm of S4 on phi1, phi2, phi3. Okay, and then you get phi4. So similarly, you just go on and you get all the phi k's that you need to define the set of all the signals. And we have used the projection terms in all these calculations. So basically, the general expression for the projection of Si over the norm of Si on phi j is basically Si divided by norm of Si multiplied with phi j and then integrated over all values of t times phi j again. So basically, this is the correlation rho ij between Si divided by norm of Si and phi j times the phi j again. So I will explain this with a diagram, what is happening from a vector perspective. Okay, so so let's first look into this entire algorithm from a math point of view, and then I will explain what is happening actually from a vector perspective. So we start with phi 1. We initialize phi 1 as s1 divided by the norm of s1, and then we define phi 2 prime, which is s2 divided by norm of s2 minus the projection that s2 might have on the phi 1 axis, and then you normalize phi 2 prime to get phi 2. Okay, then you calculate phi 3 prime, which is s3 normalized by dividing it with the norm of s3, and then you are eliminating all the projection of s3 on phi 1 and phi 2 axis, and then you obtain phi 3 by normalizing phi 3 prime by dividing it by the norm of phi 3 prime, and then it goes on. So you, generally speaking, you get any phi k prime as sk divided by the norm of sk minus the projection of sk divided by the norm of sk on all the phi j's that are obtained from step 1 to step k minus 1, and then you get phi k prime. And then if you normalize phi k prime by dividing it by its norm or by its energy, so you get phi k. So basically I should have written it here that norm of, let's say, any vector, let's say phi k prime, is basically the integration of phi k square from, so this is basically square of the norm. Okay, sorry, square root of the energy, which is the norm of phi k. So in that way you get all the phi k, and you stop when you get a particular value of phi k equal to 0. So let's say if I go iteratively from phi 1 and then I calculate phi 2, I calculate phi 3, and then suddenly at some point I get phi 4 equal to 0. Okay, so that is the stopping criteria. When I get phi 4 equal to 0, then I have to stop, and my basis functions are phi 1, phi 2 and phi 3. So 3 basis functions are good enough to represent the set of signals that I have. So generally speaking, if I have any phi k equal to 0, I have phi 1 to phi k minus 1 as the set of complete orthonormal basis functions that can represent the set of signals that I have. Okay, now let me explain this from a vector perspective, like what is happening. So basically in Gram-Schmidt procedure, what is happening, let's say you have a vector, you have a signal S1. Let's take example of two signals S1 and S2, and let me explain diagrammatically through this animation what is happening from a vector's perspective. So S1 is your first signal, let's say, and it has a direction, okay, as shown by this arrow. Okay, so now I don't have any reference. I don't know what is the relative position of this S1 signal or the vector that is representing this S1 signal in the set of axes, so phi 1 and phi 2. Okay, so I will calculate phi 1, phi 2, or phi 1, phi 2, phi 3, whatever we need to represent these two signals S1 and S2. So in Gram-Schmidt orthogonalization procedure, we start with S1 as you just saw, and we initialize our phi 1 as S1 divided by the norm of S1. So basically we are defining the unit vector, that is phi1, across along the direction of S1. Okay, so we are defining phi1 along the direction of S1, or in other words, S1 is aligned with your phi1 axis. Okay, so this is the first step of the Gram-Schmidt procedure. Okay, now now we have a reference point. We have the phi1 axis, and let's assume that we have our origin, which is denoted by the black dot here. And then let's say my S2 is this one. Okay, so now I have to find out phi2. We have found phi1, which lies along the direction of S1. Now I have to find phi2, and S2 is given here, the relative position of S2 with respect to S1. So all we need to do is to define an intermediate vector which is S2 divided by the norm of S2, and then we draw the projection of this vector S2 divided by the norm of S2 on the phi1 axis. Okay, so this projection is given by this green arrow. So the projection of S2 divided by the norm of S2 on the phi1 axis is given by this green arrow vector. Okay, so now I define a vector which is basically the difference of this S2 divided by the norm of S2 and the projection of the same on the phi1 axis. Okay, so basically I get phi2 dash, or in other words, if you recall the vector addition rule, you know the parallelogram law of vector addition. So if you have two vector, let's say the green vector, which is the projection of S2 divided by the norm of S2 on the phi1 axis, and the perpendicular vector phi2 dash, then the sum of these two vector is basically the perpendicular bisector, or sorry, just the bisector. The resultant lies across the bisector of these two vectors, and that is your S2 divided by the norm of S2. So in whichever way you want to look at it, so we wanted to find out the projection of S2 divided by the norm of S2 on the phi1 axis, and then we wanted to find out the difference between these two vectors, which is phi2 dash. So that is perpendicular to the green projection vector. Okay, or in other words, the phi2 dash vector and the sum of the phi2 dash vector and the projection vector represented by this green arrow makes the resultant vector S2 divided by S2 prime. So one way or the other. So we now we obtain phi2 dash. Now the only step that is remaining is to normalize phi2 dash by dividing itself with its norm. So phi2 dash divided by phi2 dash's norm gives you the phi2 direction. So this is how Gram-Schmidt procedure works for two signals S1 and S2. So basically we are trying to find out a set of perpendicular axes phi1 and phi2 with respect to S1 and S2. Okay, so that we can represent S1 and S2 as two vectors on this vector space defined by phi1 and phi2, or the signal space defined by phi1 and phi2. So this is the whole concept behind the Gram-Schmidt procedure, and you can you can generalize it for any number of signals through this algorithm. So you have phi1 first, then you calculate phi2, and then you calculate phi3. So every time you start calculating a new direction or a new basis function phi k, you are trying to remove the projections of all the other directions on a particular signal. So that's what is happening. Let's say when you are trying to find, let's say, phi2 dash, you are removing the projection of s2 from phi1. When you are trying to calculate phi3 dash, you are trying to remove the projections of phi1 and phi2 on s3 from s3. So this is the intuition behind the Gram-Schmidt orthogonalization procedure. So I'll stop here, and we will solve some examples to clarify these concepts of signal space and Gram-Schmidt orthogonalization in the next video. Thank you.